Okay, so we're gonna finish this week um, with a couple more things that are gonna complete your, say, calculus education. So the first one is a very important theorem that you didn't have the tools back then to actually prove. You had not constructed the real numbers, and so such you didn't know that it satisfies a very important property that you actually need to use in the proof. So everything you must have seen before was hand waving for the most part, but now we can actually introduce it and give it as a theorem. This is the intermediate value theorem. So this is known again as the intermediate value theorem. And there are multiple proofs of the theorem. All of them, of course, make use of the continuity, which is one of the hypotheses. And also of the fact that the real numbers satisfy the least upper bound property, the action of completeness, which are the same thing basically, so they're both equivalent. But you need that, so that's why I said that before. If you didn't make any mention of that, then of course you didn't actually prove this property. This is actually needed. If you try to do the same thing for functions defined on Q, then you will not be able to conclude and the result is false. So you start with a real function f, a real valued function f defined from a closed interval. So this function goes from this closed interval ab to r, including the endpoints, of course. It's a closed interval, and you assume that it's a continuous function to be a continuous function. And you need to assume that they're continuous. You can see continuous. Be continuous, and then we need to assume that there's a value between the values f of a and f of b. So then, if L, so if there exists some L, real number, such that f of a is less than L, less than f of b, that implies immediately that f of b is greater than f of a, therefore they're not equal to each other. So this is one of the assumptions. Or f of b, the same thing is valid if f of b is smaller than f of a. So if f of b is smaller than L, smaller than f of a, then there exists a point C in AB where f of C is equal to L. And so the situation you're drawing is this one. So you have A, B, and some function defined over here. Inside this interval, this is f of A, This is f of b. Then for any value L in between f of a and f of b, you'll be able to find at least one c, one value in between a and b, such that f of that point c is equal to L. So the function maps c to L. So this is so these are possible values of c. The theorem just tells you that there's at least one value of c. It doesn't tell you there's one. There's only one. Okay, for the proof, I mean, I'm just going to leave it to you as an exercise. This is not, I mean, there are several proofs of this fact. One is proposed as an exercise here in the textbook. I'm going to give you a hint for one, I mean, for one proof. Just consider in between A and B, consider the supremum of all the x's between A and B, such that f of x is strictly smaller than L. And what can you conclude about that point? You need to, of course, take a sequence inside that set and use that somehow. I mean, to use the continuity and prove that f of x n has to converge to f of c, but f of x n has to be converging to L. And how do you know that it has to be converging to L? How do you know yeah? So how can you prove then that that f of c then it has to be equal to L? Of course, I mean you have to play with continuity and with the fact that the real numbers are complete. I mean this is already used in the fact that you're defining something that's a supremum, because that exists, because that set has an upper bound, at least upper bound, and you know that it cannot be equal to b, right? Because at b, when x is equal to b, f of f is strictly bigger than L, and so there is a neighborhood around it where f is strictly bigger than L. And you know that if you cannot approach a point, then that's not your supremum, right? Yeah, no, so that's not. So of course this is heuristic at this point, but you can make it regular. So basically, near the point B, f is very close to f of b, which is greater than L. So the supremum must be achieved before. So all those values are strictly, I mean, all those values are such that f of x is strictly bigger than L. So they're not in the set where you're taking the supremum. Okay, so the supremum must take a smaller value. It has to be separated from b, at least. Okay, so some number in between, strictly between a and b, and try to conclude then the argument then that point should be a point such that f of x, such that f of c is equal to L. Okay, so that's basically everything we need to talk about with respect to section 4, I mean the chapter 4. Now I had given you, I have assigned you the reading of big part of chapter 5, and which is, I mean, again, which is again a review of calculus. Now, I told you to read everything up to Darboux theorem, basically. So this is where we're gonna pick up. So we're gonna go to section 5. Remember that we started, that I told you, I told you to start reading chapter 5, as it would be a good way to refresh your memory about the fundamental theorems. And of course, the chapter begins with a discussion about the derivatives being continuous or not. I mean, there are several examples here. There's one example, for instance, of what it shows you that many of the things that people doing calculus tend to believe are not true. For instance, if people tend to think if g prime at a certain point is greater than 0, or a point, so let me make it more specific, that a point A is greater than 0, then g is increasing near A. And this is false. Right? So this is, I mean, there are examples that are constructed explicitly in the book involving, say, x over 2 and say x times sine of 1 over x. That function is differentiable at every point. However, I mean, and it's positive at the origin. However, it's not increasing nor decreasing in any neighborhood containing the origin. Okay, so that's basically it. And well, then there's several functions like that that do that. Maybe I got one constant wrong or one exponent wrong, but that's the idea. So that you have to be careful with this kinds of statements, or maybe you're carrying misconceptions from Calc 1. But so that's why I asked you to read everything up to the Darboux theorem, not including that. Of course, the notion of differentiability is given by the limit, the traditional notion of limit, the limit when h approaches 0 of f of x plus h minus f of x divided by h. And things that you need to know. Things like theorem from 5.2.3. This was also given to you in Calc 1 as a property of differentiable functions, and you used it plenty of times. If g from a to r is a continuous function, I mean it's differentiable, say, I'm sorry, then it is continuous. If it's continuous at a point, then it is, I mean, if it's differentiable at a point, it is continuous at the point. Right, so this is something that you know from Calc 1, and the proof is what you would expect. I mean, if you're computing the limit of g of x minus g of c, so x approaches c, and that should be equal to 0 if the function is continuous. But to do that, I mean, to find out whether that limit is 0, you divided by x minus c and multiply by x minus c. This is actually going to, is approaching the derivative of the point of g prime of c as x approaches c, while this is approaching 0. So by the squeeze theorem, this is bounded. I mean, this is just a constant. So these quotients here are going to be within, say, 2 times g prime of c and 1/2 g prime of c, if g prime of c is not 0. Otherwise, of course, everything is going to 0. But since this is equal to g of x minus g of the point c, this shows that this difference goes to 0. Again, since x minus c is going to 0. So a derivative is, I mean, a function that's differentiable at a point is always continuous at the point. Now you also have all the properties, I mean, like linearity of the derivative. So if you compute the derivative of the sum of two things, then you obtain the sum of the derivatives. The quotient rule, multiplication by constant, the chain rule, and etc. Those are things that you did again, you did in Calc 1. And all those proofs that you got in Calc 1, if you looked at the book, I mean, they can all be extended, I mean, the same way. I mean, we're just lacking a few things for the proof to be rigorous. But now you have all the tools. So I'm also going to be assuming something that you use plenty of times when you remember that everything, the whole point of the calculus course, the first calculus course, is to reach optimization problems. So being able to solve, I mean, maximizing a function or finding the minimum. And you had a set of the rules. One was that if a function is continuous and different and it's continuous in a closed interval, and it was differentiable in the interior of the interval, then to find minimum or maximum, you need to check critical points or the endpoints. And why was that? Because of something that is called the interior extremum theorem. F differentiable on an open interval, then if f attains a maximum at some point inside, I mean, in the open interval AB, then f prime is 0 at that point. And the same thing is true about a minimum value. Now you can combine that. I mean, this is just again from Calc 1. Combine that with the fact that there has to be, I mean, if you're looking at a compact set, then there has to be a minimum and a maximum because of the theorem, I mean, that we learned in the compactness section. So the image of a compact set is compact, so the minimum and maximum are attained. And now you can also then derive Rolle's theorem. So what is Rolle's theorem and the mean value theorem? Now, the theorems to tell you that if a function is such that a function is such that at the endpoints of an interval, f is the same, so f takes the same value at the endpoints of an interval. Then if the function is differentiable inside the interval, then at some point in between, f prime must be equal to 0. So that's Rolle's theorem and the mean value theorem. So you consider the quotient f of b minus f of a divided by b minus a. Then in between a and b, there's a point c such that the derivative equals this quotient. So the secant is equal to the derivative some point in between. So this is slope of the secant is equal to the value of the derivative at some point. So at this point C, for this particular function, prime of C is exactly equal to this quotient. To this quotient here, so too. So the slope here happens to be equal to, the derivative at some point in between A and B is equal to the slope of the secant line, at least for some point. And that's the mean value theorem. That's this mean value theorem. But the property here, the kind of surprising property that is our Booth theorem, is the following. This theorem 5.2.7. And he says that if f is the differentiable on an interval, it says the closed interval in the book, but that's kind of wrong. To write for differentiability, you need to have to speak about the differentiability of a point. The point has to be in the interior of the domain. And now the assumption is alpha satisfies f prime of A is less than alpha less than f prime of B, or if f prime of B is less than alpha less than f prime of A, then there exists a point C in AB such that f prime of C is equal to alpha. So what's surprising about this theorem? So here we know is that f is differentiable on the open interval. And differentiable on the open interval, we also need to assume that it's continuous on a effect now, so that the way it is stated was wrong in the book. So what we need is that there is an epsilon Otherwise, the notion of differentiability would not make sense. Even if you try to speak about one-sided limits, it's not strictly correct. So for some epsilon greater than 0 on interval a minus epsilon, b plus epsilon, if alpha satisfies that is between the values of the two derivatives, here well, we're implicitly assuming that f is differentiable at these 2 points. Then there exists a point in between, so that f prime of c is equal to alpha. So why is this surprising in a way? Because f is differentiable. The derivative is not assumed to be continuous. So if f prime is a function, so you can call that g if you want. And if g takes in a value, I mean, g is continuous, and there's a value between alpha or L, as in the intermediate value theorem, between g of a and g of b, then you will be able to conclude that at some point in between some point c in between a and b, g of c would have to be equal to alpha. Also, that will be a natural proof. That of course holds if f prime or g in this case is continuous. But here we're just assuming that f is differentiable, nothing more. The derivative can be discontinuous. However, we still have this intermediate value property, regardless whether or not f is, f prime is continuous inside the interval. I'm just going to give you, again, a sketch of the proof, and I want you to complete the details. I'm going to ask you to do, to do this for the exam. So the first thing is to do the reduction. So first reduce to the case that if f prime of a is less than 0, less than f of prime of b, then there exists some c in between a and b, such that prime of c is equal to 0. Okay, so you can reduce it to that. So here, this is the first step. I'm going to put 1. Step 1 is to reduce this to simply showing that if f prime is negative at some point and positive at some other point, then at some point in between, f prime has to vanish. Then the second step, in this actually the first step is done in the book. So now to show that this is true, the reduced statement, let's take a look at this graph here. I'm saying that f prime again, there are several proofs, just like before, of this theorem. I'm just gonna give you let's sketch the proof. One of these proofs. And this is not the only way to show this, but this is one way for sure. So what about this? So f prime being less than 0, it means that the slopes of the secant lines are approaching a negative value, right? If you look at the definition of the derivative, that implies that there's a point where there's a point. So if f prime a is less than 0 implies that there exists a point x in between a and b, that is such that f of x is smaller than f of a. Similarly, f prime of b being greater than 0 implies that there exists a number y in a and b such that f of y is smaller than f of b, f of b. And how do you combine these two things? So suppose that there's a number, so that you pick the smallest of these two, f of x and f of y. So suppose there's some number over here. Then you know that the function takes on the value f of a, takes on the value f of b, but takes on also this other number here, which you're going to call z. Z is going to be x if f of x is smaller than f of y, or y if f of y is smaller than or equal to f of x. Okay, so at this point z divides the interval into 2. And remember, the function is differentiable. Function is differentiable, therefore continuous. So this this interval here from z to b, this is just a drawing, but you can, it works if f of a, say, is bigger than f of b. If f of a is equal to f of b, then the result is immediate. But so the point here is that since the function is differentiable, it is continuous in between c and b, and therefore you can apply the intermediate value theorem. So at some point, this will take on the value f of a. Right? Because z is smaller than both. F of z is smaller than both f of a and f of b. So that means that there's a point in between where between C and B, such that this point at this point f is exactly equal to f of takes on the same values as f of a. So the value at this point is exactly equal to f of a. Therefore, you may apply the Rolle's theorem and find a point in between where the derivative is 0. And then you're done. So I'll leave the details to you then to complete. But this is all the elements are here. So you divide the interval into 2. You choose, you proving these two properties. And you choose a value, the smallest value between these two, so that you can apply them. You can divide the interval into 2 and apply the intermediate value theorem. Find a point where the function takes on the same value as one of the endpoints, and restricting to that smaller interval from a to this point, say, then you can apply Rolle's theorem and conclude that there's a point where the derivative has to vanish in between. And that's it for this week. So have a nice, good Thanksgiving break.